Okay, so continuing from the previous session, we are going to continue again about some applications related to the use of resistance-based sensor in biomedical application. So this is what we had discussed last week about we had started to discuss last week about the use of resistance measurement, resistance-based sensor to measure the volume of bladder in patient with urinary dysfunction. So normally the bladder volume is done either using can be measured using ultrasound instrumentation. Of course, if you use ultrasound instrumentation, then the measurement cannot be done in real time. The patients need to go to the hospital or to clinics which have ultrasound device. Then also after you do the measurement, you need to do some processing to the graphics or to the images obtained from that in ultrasound imaging. Okay. You could also use pressure sensor and also bioelectric impedance measurement. However, the problems also for ultrasound, among others, besides that it cannot be done in real time, there is also possibility of interference or defects. Yeah. In ultrasound imaging, there could be many artifacts, we call it, in the imaging due to the motion of the patient, for example, or any other sources which may interfere the measurement. So one of the solution that is researchers have proposed is the use of an implantable sensor, and the implantable sensor is strain-based sensor. Yeah? So it measure the strain of the bladder due to the expansion or contraction of the bladder volume. And the strain-based sensor is based on polypyrrole. So polypyrrole is the type of conductive polymer, and it can be made flexible by depositing it onto a flexible substrate. So this is the video about 3D bladder volume measurement using ultrasound. I think I have displayed and I'll show it to you last week. And then so this is the device. The polypyrrole wire are being coated onto this substrate, flexible substrate, strip lines of polypyrrole wire. Actually, similar device has been used to measure also the volume of heart, for heart failure problem. And this is the implantable circuit for reading out the sensing parameter. As you can see here from the circuit, it has the current amplifier, and then a sensing resistor. This is the sensing resistor, which will change or adjust the resistance change will then adjust the current flows into this operational amplifier, and then when it is above certain value, it will trigger, and this will trigger to and then being transmitted to the measurement system. Okay, then let's go to the next type of resistance-based sensors. So last session, in previous slide, we have discussed about mostly the resistance-based sensor, strain gauge, that is made from thin metal film or thin metal foil, and a conductive layer, a conductive thin film being deposited onto a substrate. If it could be metal, chromium or platinum deposited onto, for example, polyimide, like the common strain gauge that we found in the market. And another example is the use of piezo resistive sensor. In piezo resistive sensor, if we see from the formula, the formula of resistance, R equals to rho, L/A. So in this case, then delta, 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 R, yeah, could be could be a function of delta rho, delta L, or delta A. Okay. So in metal foil strain gauge, the main sources of the change are usually the L, the dimension change of the conductor itself, either the length change or the cross-sectional area change of the conductive wire. So in polypyrrole, as we just saw in the previous example, it is a conductive polymer. So when the bladder expand, the length will change, yeah, due to because it has this small Young's modulus, yeah, small rigidity modulus, Young's modulus E, because it is polymer, yeah, as you have learned also from biomaterial. Polymer material have the lowest of Young's modulus compared to the other types of material, metal or ceramics or composite. So on the other hand, when we speak about piezoresistive sensor, what changed most is actually this delta rho. So delta L and delta A may be not that big. Yeah, there is also delta L, there is also change of length or change of cross-sectional area, but most of the time it is function of the delta rho. Yeah, so delta rho here, rho, the resistivity basically is the characteristic of the material itself, yeah, the resistivity of silicon, silicon carbide, germanium, etc. So the material could be monocrystalline silicon, polycrystalline silicon, amorphous silicon, silicon carbide, or germanium. So as you can see here, many of them are basically semiconductive material. Yeah? So when they are monocrystalline, then the resistance change is due to the elongation, yeah, in the crystalline structure, between the distance of the atom. If it stretch, becomes distance from each other, so that it takes more time, more length, more duration for the electron to travel from one atom to another. As on the other hand, if it is compressed, then it is closer to each other, then it is then faster for the electron to travel between atoms. In the polycrystalline silicon, on the other hand, the piezoresistivity is more affected by the intergrain spacing or intergrain interface. So when the grain, the different crystal grain, so the neck, usually the neck, what you call as the neck phenomena. So when they are stretched, so there are more space between the neck, so it takes some more time for the electron to travel between one grain to another grain. I think the value of which you have done, yeah, in the previous quiz. In one question of the previous quiz, there is a question where you need to compare the sensor properties between different type of sensors, you know, type of strain gauges. And one of the strain gauges is polycrystalline, the other one is monocrystalline. These materials can be fabricated using integrated circuit technique, microfabrication, and MEMS technology. Okay, and that's why it is not that cheap. Yeah, but overall, it is not that cheap. But if you within one single batch of processing, you can fabricate many devices within a single wafer of silicon. Then the price per single chip, yeah, per single device will be a very cheap, yeah, very low cost. That's why it is useful if you want to make the sensor in mass production. So application of piezoresistive sensor, it can be used in pressure measurement, where it is being attached or deposited on the diaphragm or membrane. Then also measurement of other parameters that can be converted into pressure. The changing of electrical resistance of material due to the applied mechanical stress Yeah, delta rho over rho, delta rho over rho. So delta rho over the previous the initial rho equals to the pi times the sigma. So sigma is the mechanical stress. Yeah, remember from mechanical. So from biomaterial, sigma is the mechanical stress applied to that resistor. Pi is the piezo resistivity coefficient. Rho is the conductivity of the material. Okay, so then the sensitivity of the piezoresistive device is characterized by gauge factor, GF. Okay, and delta R over epsilon. So that is why when you calibrate a strain gauge, yeah, or piezoresistive device, the x-axis you with always you usually make you calibrate against the epsilon or delta L over L0. Yeah, remember the definition of strain, yeah, in the biomaterials. So you stretch or you compress the material, the that change relative length change of that material compared to the initial length. Then this the y-axis you don't measure it against directly the r, the value of r, but instead r minus r0 divided by r0. Okay, or this is equals to delta r over r0. So you then try to plot the dots. Okay, yeah, of course you have to do it with multiplicate measurement. Yeah, then you draw the calibration curve. Okay. You draw the calibration curve. Then from here you obtain the gradient delta y, which is delta y here is delta r over r0, and this is epsilon. Okay, delta epsilon. Okay, so the k, the sensitivity is the gradient of this line or limit of delta epsilon approaching 0 divided by, yeah, or the delta r over r0 divided by the epsilon. Okay, the derivative. So this is the how we get the gauge factor of a piezoresistive device. And normally and usually when you purchase a piezoresistive sensor, this parameter should be given. If you make your own piezoresistive device, you have to also calculate this by calibrating this. You stretch, you put the sensor on certain material, which you know, and you stretch or you compress it, and you can calculate the strain, yeah, or you can actually, you can also apply flexural bending, where you can calculate also the bending strain based on certain formula, and then you can draw, then you measure the delta R over R0. After that, you plot it against the epsilon to calculate the sensitivity. So this is how it looks like, yeah. In this is, for example, I think, yeah, the diameter, sorry, not the diameter, the length, total length could be as small as 5 millimeter, for example. So this one could be as small as 2 millimeter by 2 millimeter. Okay, that's small. So here, if you see individually, so this is the component of the piezoresistive device, piezoresistive sensor. So this piezoresistive device, there are 4 of them, and they are attached on the square membrane. So if we draw from cross-sectional point of view, it will look like this. There's a membrane here, very thin. This is the middle one. This is this part. The membrane part is this middle. Okay, and this sensor, the piezoresistive sensing device, is draw it with another line, another color. is here. Yeah, so it is at here on the usually on the edge of the membrane, on the neck of the membrane. Then they are connected then using conductive material like aluminum, for example, like aluminum. So this is the aluminum electrode, and then the piezo resistive devices is this part, the small part here, and the blue one there is membrane. Yeah, the membrane. Usually it is made from silicon nitride material or silicon carbide or just silicon. Okay, so when there is pressure, yeah, when there is pressure, for example, the pressure here is different than the pressure from this side, then the membrane will deflect. Okay, the membrane will deflect. For example, if P1 is less than P2, the membrane will be like this, bulging upward, right? Okay, so what will happen here? So this part of the membrane will endure or will feel a compressive stress. Yeah, will feel a compressive stress. So this one uh, will be a compressive stress. We call it negative, right? Compressive strain, negative strain. While this part on the middle will feel a tensile strain, but there is no piezo resistive device put in the middle. Yeah, but some device could make it also their design that there is a piezo resistive device attached here. Okay, so if you look carefully here, this device is made. Yeah, this device is made as very tiny connection like this, like this. So you should draw it in red. Yeah. And then this is connected to the electrode, the larger electrode. Okay. So by putting this four piezo device in a whetstone bridge, then you can measure the strain caused by that pressure. If, however, P1 is larger than P2, then what we will have is that the membrane will be deflected downward, right? So it means then this one, the place where the piezo resistive devices are located, will feel tensile stretch. This one will feel tensile stretch. Yeah. So then it is depending on the gauge factor. If the gauge factor is positive, then resistance will increase. If the gauge factor is negative, then in this case, yeah, the resistance will decrease. Okay, so this is how a pressure sensor works. Pressure sensor that is using resistance-based sensor. There are also pressure sensor that use capacitance-based sensor, which we don't later we will also maybe discuss. There. Okay. So piezo-resistive measurement, semiconductor materials are temperature sensitive and non-linear. Yeah, that is why that usually in order that we can that we can reduce or we can eliminate the effect of temperature, we also put not only here, but we also put this kind of the same device, yeah, somewhere outside, somewhere here or somewhere there, yeah, where it will also have, it will change due to the temperature change, but it will not be affected by this pressure change. So why is that? So that it to compensate the temperature sensitivity of that piezo resistive device. So resistor network can compensate for offset drift, and full scale output drift as well. Yeah, the resistor network. So an example of resistive based network, circuit network that can be used to tap the signal coming from those four resistance, yeah, base sensor, piezoresistive sensor in a bridge configuration is like this. So we have here a constant current source. Basically, then since we have RDS here, there will be this one becomes a voltage source. Yeah? You can also change here with a single voltage source depending on what you have. So we have here the excitation voltage. Yeah, so basically similar like this is whetstone bridge, basically a whetstone bridge configuration. So you put the four piezoresistive devices in the four arms of the resistor of the whetstone bridge. Okay, then as to trim to null to balance the offset, yeah, due to temperature or due to other things or due to the resistor itself, to the inaccuracy of the initial resistance values of the piezoresistive device, we can put this zero trim resistor. Yeah, usually these resistors are potentiometer where we can tune, we can adjust to nullify or balance the bridge. Remember the formula for whetstone bridge, yeah? In order that so that when there is no stimuli, when we calibrate, when the pressure is P1 equals to P2, then uh, this output of the whetstone bridge should be zero. Okay, the output voltage of this whetstone bridge should be zero. So this excite the whetstone bridge. When there is no resistor, when there is no pressure, the resistance change at all the four piezoresistive devices should be zero, and the signal plus should be equal to signal minus. So the amplified output should be zero. But when there is resistance change, when there is pressure, so for example, as shown here, P1 is less than P2, the diaphragm will bulge, right? And the piezoresistive devices, the four piezoresistive devices will feel negative strain or compression if the gauge factor is positive, yeah, then the resistance will decrease. Yeah, all the four resistors will decrease, and we will feel all the four will be amplified as amplified voltage here. Okay. RDS resistor is used to stabilize this one, the sensitivity by shunting an increased amount of excitation current as temperature rises. So when, yeah, this is to compensate for the temperature. When temperature rises, usually then resistor will rise as well. Okay, so as a result, the voltage here will, the excitation voltage will also increase. So that then the resistance change due to the 4 will also be compensated. The RTZ works against the offset, the change of offset with temperature, as I mentioned, by trimming this resistor, the two of either of these two or both of these two, we can make the signal to be zero, so that then we can offset, we can nullify the offset due to temperature or other interference signal. So this is the advantage, main advantage of using a whetstone bridge to as a secondary transducer to convert resistance change from the piezoresistive device into voltage change. The main advantage is that it can, we can we can nullify the offset. And offset is something which we do not want. Yeah? So offset is something which we do not want. So remember offset. So when the stimuli is 0, for example, this is pressure and this is delta voltage here, the amplified output. What we want is the volt delta V also should be 0, right? Then it increases linearly with the increase of pressure. However, if we don't have this zero trim resistor, what we will have is that we might end up having an offset here. Even when there is no pressure difference, there is already delta V. This is what we call as offset. Yeah, remember the sensor characteristic chapter on the previous chapter. So this is another example of electronic circuit that we can use to tap into the four piezoresistive devices. Okay, for piezoresistive devices. Yes. So the change will excite here input positive, this one input negative, put into programmable gate array, whose programmable gain amplifier, programmable gain amplifier, whose gain can be tuned to apply appropriate gain so that the end output is readable. The current source comes from here. This goes to this one, the CA, the buffer. So controlled current source for driving the sensor. So this will, this one, the excitation for the Whetstone bridge comes from this one, from this current source, from this node. Okay, which implement a unique algorithm to compensate sensitivity drift. What is sensitivity drift? Yeah, sensitivity drift occurs when the gauge factor change with time. So initially maybe, so let's say this is epsilon, let's say this is pressure, because this is already made as a pressure sensor, and this is delta V. Initially during calibration at the factory, it may be like this. But after a while in the field, it may drift like this. This is original. This is change number 1. So what to do with using this? The gain can be tuned such that, because sensitivity drift is related to this gradient, so we can tune such that the gain is adjusted. So this goes back to the original factory base calibration. Okay. Any questions so far? Quite clear, yeah? So this is how in more closer look about some fabrication of piezoresistive device. This is for biomedical application. This is a type of pressure sensor. The packaging, the package inside, I forgot the name of this packaging. And this is the chip MEMS application, MEMS implementation, micro electromechanical system implementation. The membrane is made using 10 micrometer thick of silicon membrane on top of 6 micrometer porous silicon, and then covered by silicon dioxide. This is the membrane. Okay. Now here, the design of the membrane is a little bit different than the previous example. In the previous example, it is just plain rectangular. Okay. While in this configuration, it looks like this, what we call it, butterfly tie. Yeah, butterfly tie. Remember? Membrane. So the piezoresistive device is located here at the neck and then also at the middle. 2 of them are in the middle, 2 of them are on the edges of the membrane of the diaphragm. Okay. So here, this electrode connect to this and this, as well as to this and this. So this is already in Whetstone bridge configuration. Ultra-monitor resistive pressure sensor are developed to monitor intracranial pressure during surgery air pressure for respiratory disease, yeah, blood pressure during surgery or intensive care, like we had discussed last week. When it is inserted, the diaphragm is in the device where it is then connected to a catheter filled with fluid, yeah, it's a specific fluid. Could be used for intrauterine measurement, for obstetrics, as well as abdominal and urinary pressure, as we have also discussed earlier for the bladder volume measurement. Okay, this is an application of cochlear measurement. Do we have here the video? Yeah. Oh yeah, we have video here.
In case of sound waves striking the ear, they pass through the canal to the eardrum. From there, the sound waves are mechanically transmitted to the inner ear and amplified. In the inner ear, you can find the cochlea. The cochlea consists of 3 different canals. The middle canal is the organ of hearing and consists of sensitive hair cells. The hair cells can be stimulated electrically and forward the signal to the nerves and then onto the brain. In most cases of deafness, the hearing nerve still remains functional, but the hair cells have been damaged or even lost. In a cochlear implant system, sound enters a microphone and travels to an external mini-computer called a sound processor. The sound is processed and converted into digital information. This digital information is sent over a transmitter antenna to the surgically implanted part of the system. The implant will turn the sound information into electrical signals that travel down to an electrode array inserted into the tiny inner ear or cochlea. The electrodes directly stimulate the auditory nerve, sending sound information to the brain. Bypassing the damaged inner ear, the cochlear implant provides an entirely new mechanism for hearing.
Okay, so this is an example how a cochlear implant is made, yeah. So, but then the problem is, how do we know where the whether the cochlear implant is already in the correct position? So that is why what they use here is a strain gauges that is located at various position within this flexible cochlear, yeah, in order that it can be able to measure its position relative to within the cochlear implant. Okay, so this is how it is being developed using also MEMS technology, microelectromechanical system. Yeah, and the Pso Resistive Sensor here in this case is being implemented using polycrystalline silicon. Here it is deposited at various position. So when it bends at that various position, then it will send the signal. So then the implanter, the doctor that you do the implantation of this device know whether the cochlear implant has been bended, folded, or bended, not folded, to the correct position within the implant, within our cochlear. So this is one implementation from Professor Wise in Michigan State University, like this. Yeah. Another implementation. So here the resistive sensor strain gauge are located along this flexible thin metal foil. This is a wearable yarn sensor used to measure the breathing, yeah, for babies. For babies, in the yarn-based sensor is embedded inside the inside the what the belt, yeah, the belt that is being worn by the babies, and inside it is when the babies expand, or not necessarily babies, yeah, or adult, then it will stretch, and the sensor, the resistance will change like this. So this is the equivalent circuit of the belt, the equivalent circuit of the elastic band, and this is the reading circuit, the secondary transducer to read the resistive change. This is one indicated by R4. Yeah, it is located inside within these forearms of Whetstone bridges. So then the respiratory band can be connected, yeah, to a lung model, yeah, and then it can be also used to monitor the respiratory function of the patient with inside a ventilator. This is how the signal will look like in wearable yarn sensor. This is a beat per minute. This is the standard. Breath per minute. This is how it looks like during inspiration, and then this is the stage of inspiration. The voltage increase, indicating that the chest expand. Right, the chest expands, so that then the resistance increases. The delta V also increases. During expiration, this part, yeah, the chest contract again, the volume contract. Then the piezoresistive yarn decrease its resistance again, like relax again. Are there any questions so far? Related to piezoresistive device?
Yang shape-nya kayak butterfly itu, what is the advantage of that kind of shape?
What is the
Advantage of using that kind of shape daripada yang satunya lagi?
Let's see, this one. Yes, it may, because then you could put them in the Whetstone bridge. You could put them in opposite arm of the bridges, because in this part, for example, if it expands, yeah, if it bulge, yeah, when it bulge like this, okay. So the one in the edge will have negative, yeah, strain or compressive strain, while the one in the middle will have positive strain or being stretched. In the Whetstone bridge, you could put them in opposite. Yeah, for example, this one is for the positive, this one for the negative. Usually in the Whetstone bridge, this will advance, will amplify to each other. If you derive the equation, then the amplification due to this will be 4 times the delta in this configuration, rather than if you only put at the edge, like in this device. In this device, you only have, if you put in the formula of Whetstone bridge, I think about 2 times of the delta R over R times the excitation voltage. Well, in this case, you will have 4, because you put the positive and negative at opposite side. Yeah, remember that in Whetstone bridge there is a negative, right? R1, R2, negative R3, R4, for example. Divided by R1, R2 plus R3, R4. This because of the negative. If negative minus negative, it becomes positive, then it becomes a larger amplification factor to transduce resistance change into voltage change, in comparison with if it only negative only, for example. Is it clear enough?
Yes, sir.
To be clearer, you need to derive the equation for Whetstone bridge. Yeah, so then you will understand better.
Yes, sir.